Hello and welcome to today's webinar. Today we will look at connecting AC inputs to Horner OCS. Let's look at our agenda for today. We are going to start by answering the question, why AC inputs in 2025? Now we are going to give you some AC inputs examples, and then we are going to show you how to integrate AC inputs with I/O that is built into the Horner OCS all-in-one controller that appears to be DC only. Then we are going to show you how to connect AC inputs to OCS-I, that is Horner's expansion I/O system, and there will be demonstrations throughout, and we will finish with a Q&A session. Why AC inputs in 2025? We talked about all the good reasons why we would use DC on a regular basis. However, sometimes we have some projects like a machine retrofit where there might be legacy AC sensors and that the decision may have been made to leave those sensors in place. If that is the case, then we need to deal with those AC signals that are being put out of those sensors. So how are we going to do that? Let's look at a couple of different scenarios of where we are dealing with AC, starting with those legacy sensors. On the screen there we have an example inductive prox, that is an AC only inductive prox. Nowadays most inductive proxes support either AC or DC. However, there are plenty of legacy sensors that are AC only, and we need to be able to interface with those. Another scenario where we are dealing with AC is where we have a series of circuit breakers and we want to tap into the wiring after the circuit breaker so we can detect whether we have a current flowing through that wire. So another scenario is the output of a circuit breaker where we might want to tap into the AC signal and be able to interface that with our control system. So these are just a couple of different scenarios. When we have a Horner OCS with built-in I/O, and it is all DC inputs, we connect those AC inputs by using a device called an opto-isolator. An opto-isolator is a compact DIN rail-mounted device which effectively completely isolates an AC input signal from the DC input circuitry built into Horner's OCS and converts that AC signal over to DC. You may simply use one opto-isolator per AC input, and then you can mix and match between DC input signals and AC input signals. Simply putting the opto-isolator in between any AC input and one of the DC input terminals. Now you can acquire them from a number of different locations for interfacing an AC input signal with a DC only input circuit. These are the way to go. Another advantage to the opto-isolator is that they support voltage all the way up to 240 volts AC. So if you are using higher voltage like that, you are most certainly going to need to use an opto-isolator. Now for our demonstration, we are going to start by taking a look in the waveback machine of an opto-isolator connected to the micro OCS. Here is the AC side. This is where we could connect our AC signal that we want to detect or send. This terminal, the A2 terminal, that is where we are going to connect. The neutral as the reference for A1. You have an optical isolation here in the center, and then this is our DC side with the positive output pin here and the common output pin. We have actually wired this up, so there is one on the right here, and we are using the circuit breaker here with a manual switch on it to kind of switch an AC signal. So we have got a hot signal running into the top of the circuit breaker, running down the circuit breaker and into the opto-isolator. We have got a neutral coming into the opto-isolator as well. On the other side, we have got our DC connections, and then coming out of our DC connections on the other side of the opto-isolator, we have this orange wire here that is wired into a digital input on the micro OCS. In this case, it happens to be I1, so we will take a quick look at the screen here, and you can see we do not have any power happening here, or the voltage is off effectively. So if we turn on the breaker, you can see we get an indication both on the physical device itself, on the opto-isolator itself, and then we also got the micro OCS sees that as A1. We are going to take a look at that scenario where we want to connect those AC signals to an external I/O. In this case, Horner's OCS-I. Now if you are not familiar with OCS-I, OCS-I is Horner's newest expansion I/O system. It mounts on a DIL rail And it just so happens that there is an AC input module available for OCS-I. So the way you integrate OCS-I is you start with the base, and there are two different bases available. One base that strictly provides a connection to your OCS with no built-in I/O of its own, and the other base component which offers not only the connection back to OCS but also offers built-in I/O. And then once you have started with your base component, you can add either 7 extra I/O modules per base, and you can have up to 16 bases per system. So it is a very scalable system. One of the advantages of OCS-I/O, besides its variety of DC inputs and relay outputs and analog type modules, is it does support an AC input module, and that is what we are talking about today. Let's take a closer look at the DIMP 620 HE959. DIMP 620, which is the AC input module that provides 8 AC inputs. Now it supports voltage up to 120 volts. So if you have voltage higher than that, you will need to use an opto-isolator. But you have got your 8 inputs. You have got a place to connect your L2 or your common type connection here. And it is really easy to integrate. Once again, it is limited to 120 volts AC. So keep that in mind, but that is a majority of what the applications are anyway. The wiring was quite simple. On the L1 side of things, you run that through the switch and then into the input. On the L2 side of things, you run that into the common terminal. Now all common terminals are on the same potential. So if you have multiple phases involved in your application, you will have to have one module per phase because of that. For our next demonstration, we are going to take a look at AC signals with OCS-I. Here is our Seascape 10 program that we are using to demonstrate connecting AC inputs to OCS-I. Let's start off in the hardware configuration because that is where you find OCS-I. Our demo system here is based on XL-W' OCS all-in-one controller, and it is connected to OCS-I over C-SCAN. So what we have here is a very simple 2-module system where the first module is the base, which happens to be the base with built-in I/O, and the second module is one of our 8th channel or 8-point AC input card. Let's take a look at the configuration of the base. We gave the base a convenient name, assigned some status variables to it, and then we need to allocate a place for the I/O to be mapped in the Horner memory structure. Now, when you are doing this, you are typically going to use some I/O arrays that have been pre-configured in Seascape. And there is an I array, a Q array, an AI array, and an AQ array. Now remember, because these arrays, they typically start at 0, the reason that we have allocated them to all start at 64 for this particular base is because our particular XL-W' has I/O built into it, and we want to make sure the I/O on the OCS-I base is mapped to a location well above the built-in I/O. The arrays being 0 based are offset by 1 from the %I, %Q, %AI, and %AQ memory addresses. So I64 correlates to %I65, also because there is an onboard I/O on this particular base, and our AC inputs are not going to be starting right at the beginning of the memory for the base. But to see where the DIMP 620 module is mapped from an input standpoint, we can go to the More Info button here, and it tells us for our DIMP 620 that those inputs start at I80 on the array side, which correlates to %I81 on the memory side. This is our OCS-I configuration, and then we could have just chosen to use I80 through I87 array input array directly to map 2 variables, but instead of doing that, we went ahead and created some separate variables called AC input 1 through AC input 8. And we went ahead and manually mapped those where the AC inputs are mapped with the OCS-I, and that is starting at I80 on the array side or %I81 on the memory location side. All we have done here is we have created a single screen with LED indications showing the status of the input. Let's take a look at the system on the bench. What we have here is L1 and L2 are hot and neutral running to the terminal strip. The L1 signal, or hot, is running through the circuit breaker, and then the other side of the circuit breaker is connected to I8 on the terminal here of the DIMM 620, and then the L2 signal, or sometimes called neutral, is this blue wire here, and it is connected directly to the common terminal on the DIMM 620. We can see here on the screen everything appears to be off. If we flip this breaker, we get our LED to turn on. We went ahead and had another LED indicator here to indicate that we have power flow there, and you can see up here in this corner we also have LED indication on the module. That concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.